Yes. We now want to deal with an advanced area of probability theory, namely conditional probability, and the concept related to it, which is the independence of two events. And conditional probability can be understood colloquially as having a condition where it is assumed that this has occurred. And under this condition, one wants to know how probable it is that another event occurs. That means we are dealing with two events, namely event B, for which we want to determine the probability, and condition A, which is to be our condition. And the whole thing is written as follows, you see here. Exactly. So the notation is such that we have a P for the probability, then we have a B, and then we have the condition A, so to speak, and then there is a slash, a vertical line in between, and we say P of B under the condition A, and there is a formula for that. We can take a look at why this formula makes sense. We determine the probability of A and B, so we examine how likely it is that both A and B occur. Why? Because both must occur in this probability, only that we then normalize again, so to speak, with probability A, meaning we divide by P. So this is definitely the way you can always calculate the probability. And at the same time, I will write this down here. You can also reverse it. You can also calculate the probability of A given condition B. And there you see that the numerator remains the same while the denominator changes. We will see again shortly why this is relevant. Let's keep it simple. Exactly. We are talking about conditional probability, and we want to look at a simple example to recognize that it is actually an easy definition and that it often aligns with intuition. Specifically, we want to look at how high the probability of rolling a 6 is under the condition that the number is an even number. And for that, let's briefly look at the two events. Event A would be the 6, and event B would be the even number. So that would be a 2, a 4, or a 6. And what you see here is that they want the probability of rolling a 6 under the condition that either the 2, the 4, or the 6 has been rolled. And they know this intuitively, namely the probability is 1/3. Because 2, 4, and 6 are equally likely, and they ask, how likely is it to roll a 6? We will also see this in the following. Let's briefly determine an intersecting B. In this case, it's easy, as it is simply the 6. Then we can say that the probability of A given B is according to the formula, the probability of A intersecting B, which is just one element, so 1/6, divided by the probability, which is 1, 2, or 3, 6. And overall, the two 6's cancel each other out, leaving us with 1/3, just as we would expect. Yes? So that is the concept of conditional probability. And the next formula we will look at is the multiplication rule, which goes hand in hand. So, if we multiply this equation here, let's take this one, by P on both sides. Then it states that P times the probability of B given condition A is equal to the probability of an intersecting B. I'll go back again. If you simply multiply the P over to the other side, then exactly that happens. And you can do the same with this formula. You can also multiply on this side, and then you will get this result here. And this is often helpful when you want to determine P, and perhaps coincidentally have P under condition A. This is the multiplication rule. And finally, let's take a look at when two events are indeed stochastically independent, or as we simply call it, independent. And there are three ways to verify that. Let me first briefly explain what we mean. We mean that whether event B occurs or not has nothing to do with A, the occurrence or non-occurrence of A, and vice versa, that whether event A occurs has nothing to do with the occurrence of B. And there are three ways to test this. And if one of the three is correct, then all three are correct. And if one of the three is wrong, then all three are wrong. That means these three properties are all equivalent. And we will take a brief look at them. Let's first examine the first condition. So P under condition A is equal to P. And why does that make sense? Well, I said that. The probability of B should not depend on event A. That means P is also equal to P under condition A, so condition A does not matter. And we can ask the same thing in reverse, namely P. And we see the condition here. Only with the roles of A and B swapped. And if we then assume that R holds for 1 and 2, we can simply apply the multiplication rule, and then it is P of B. Then this means that the probability of A intersecting B is the probability of A multiplied by the probability of B given A, and this is now the last condition that we can write down here. And as I said, it is such that all three, if I now ask them, are two events independent, then they can choose their favorite conditions and show whether it holds or does not hold to answer this question. For this, we will also do an example now. Specifically, we are looking at a six-sided die, and we have two events. So we have our omega is 1, 2, 3, 4, 5, 6. And then we have event A. The rolled number is an even number, so Uppsala. 2, 4, or 6. Or B. The rolled number is greater than 4, so 5 or 6. And now we can ask ourselves whether these two events are independent. For example, we can consider if the probability of A intersecting B is equal. So I simply put a question mark P. And we determine P of A, which would be 1, 2P. Is 1, 3, and a cut B, we see, we can quickly write here. So it is essentially basically only the 6 and thus 1/6. And indeed 1/6 is equal to 1 to 2 times 1 to 3, thus independent. And you can actually come up with another example where you can see that using the other formula to understand the whole thing is also possible, but that's enough. We are done and can now see that event A and event B are independent.